Okay, so good afternoon, or maybe good evening or good morning to everyone. So I am Alejandro Franco. I'm a full professor at University of Picardy in France. So, and I'm very happy to chair this session about artificial intelligence for data analysis, and in particular battery manufacturing data analysis. And I'm going to introduce this topic, talking first of all about the battery manufacturing process. I think all of you should be aware about that based on the presentations that you listened before. So in this manufacturing process, we have a very complex combination of steps involving multiple parameters. And then, so it's very important to develop digital twins to predict the influence of the manufacturing parameters on the performance of the electrodes, right, that are being used in the cells, right, in lithium-ion battery cells, and other properties also such as lifetime, safety, and so on and so forth. So a digital twin is a copy of this real manufacturing process in the computer, right? And the way that you can do this copy is so by adopting two types of complementary modeling approaches. So one of them is developing physics-based models describing the physical chemical processes going on along each step of the manufacturing process. Or you can also use data-driven approaches, right? In particular, machine learning. So the advantage of machine learning compared to physics-based models is that once they are trained, even if training process of these models can cost a lot of time, right? Once these models are trained, so you can make very powerful predictions in very short time, right? With very small computational cost. In contrast to, for example, a 3D-based physics model that will cost a lot in terms of computations, even though it will have very powerful prediction capabilities, right? Both approaches are complementary. And here, so I'm going to show you some examples of application of machine learning in the topic of battery manufacturing, based on the work we are doing in my group, right, as an example, right? And you will see that this can be generalized, right, for other topics. First of all, machine learning is a powerful tool to find correlations in databases with numerous dimensions. Particularly when you build at experimental level tables like this, where you have multiple inputs and multiple outputs, and you want to understand how the outputs depend on these numerous inputs, right? If you are wondering this, then machine learning models is one possible tool that you can adopt to that, maybe the most appropriate tool that you can adopt to address this kind of complex problem. Here you see an example of this machine learning model, so applied to these multidimensional data sets, in particular for the problem of slurry formulation, where here, so you intend to predict the loading and the porosity of the electrode after, so you cast the slurry on the current collector and you dry the coating, right, in the oven. And then, so you can collect experimental data, you can put it in a machine learning model, in this case, a support vector machine model, and then you can come out with very nice graphical information that can be very useful for guiding the design of these electrode slurries. In this graph, you see, for example, the influence of the formulation of your slurry, the solid to liquid ratio and the viscosity on the porosity that you expect after drying the slurry. Each color here corresponds to a different class of porosity, right? Low porosity being in white, medium being in pink, and blue being in high. Another application is of machine learning can be optimize the calendaring process of the electrodes. And this is something that once again you can do if you collect experimental data. Then you feed this experimental data somehow in an electrode structure generator in 3D that is going to localize randomly the particles of active material, carbon binder, and also pores. You can characterize these structures depending on the calendaring conditions in terms of tortuosity factor, in terms of conductivity, and so on. You can do all this in silico, that means in the computer. And then based on this data, you can train a machine learning model, this time to do a regression prediction, which is a quantified property, right? As for example, the tortuosity factor of your electrode, right? Which is related to the ionic conductivity of your electrode when you will fill the pores with liquid electrolyte. And here you see the impact, the predicted impact by the machine learning model of the pressure on the tortuosity factor as function of the formulation of the electrode, okay? And also as function of the initial porosity of the electrode before the calendering. And the numbers that you can see here with the little cross corresponds to the porosities achieved after the calendering process. You can, of course, extend all this to other type of batteries, such as solid-state batteries. And this is for another example of work that we recently published. So here, basically, you collect data for related to the synthesis of solid-state electrolytes for solid-state batteries. Here, you can play with different parameters, such as the different material contents that you have, and also the processing step parameters that you implicate in this fabrication of solid-state electrolytes. And then based on this data, so what you can perform is statistical analysis using in particular principal component analysis to compress the data set, to keep only the most relevant variables, right? The most relevant parameters, the ones that are affecting more the outputs. In this case, the output will be, for example, the solid electrolyte quality and the conductivity. And then once you do this data compression, you can apply unsupervised machine learning models to identify different type of classes, right? And then you can use these identified classes to train a supervised machine learning model based on support vector machine to build, once again, this kind of very nice graph. We can really guide the experimentalists, right? By deciding, it can help the experimentalists to decide which, for example, solid content or ratio between materials he or she needs to adopt in order to make a solid state electrolyte with high uniformity, I mean, high quality and high conductivity. You can also use machine learning to extract automatically information from scientific publications, okay? This is also a work we published recently, where basically you develop a machine learning model which is able to recognize entities in publications, and then it allows performing statistics on the way that the people report experimental data in scientific publications. We could imagine that we can use also the data available in scientific publications for training machine learning models that can help the optimization, right, of the battery devices. This is, however, is something challenging, and this is something that we found, is that basically people, they don't report systematically important properties that need to be reported in order to ensure that others can reproduce the experiments that are being reported in publications. For example, we found, thanks to this text mining algorithm, that 97% of publications, they don't report electroporosity, right? And also you can see here that 96% of papers, they don't report electrolyte volume, for example, which is very important to be reported if you are studying SCI formation, for example. So then this actually highlights the need of data reporting standards, right? And once people will start to publish things in a standardized way, then we can imagine using machine learning models that can extract this information and then doing useful things with, like discovering correlation between parameters or optimizing electro properties or manufacturing processes and so on and so forth. All these examples I show you today are in the context of a project. It was mentioned by Christina Enstrom in her presentation very nicely. The name of this project is Artistic, which is actually a project leading with the digitalization of battery manufacturing, exactly like De facto. But this Artistic project started 2 years earlier, right? It started in 2018. So it's an ERC project for 5 years. I am the PI. And here, so this digital twin that we are establishing is resulting from the combination of physics-based models and these data-driven models at the same time, okay? And the goal of this digital twin is accelerating the analysis of manufacturing data and also predicting and optimizing. This is the website of the project. There you will find web apps for simulating battery manufacturing from an internet browser. And also our target is that this web page of the project becomes a reference manufacturing open data repository, okay? This is something that is lacking in the community. And we want to share this with everyone. I mean, you can already log in the web page. I mean, create a login in the web page of the project, and you will receive automatically a password, and then you can enter in this online platform and navigate with all the data and the models that we're developing in this project from now. Last but not least, I mean, to conclude this short introduction to the topic, I would like to announce this webinar series that we are organizing in 2 weeks, starting on 21st of June. So this is Artistic Project Webinar Series. It's a second edition where we are going to have once again Elizabeth to explain the De facto project, but in much longer. I mean, she has a lot of 50 minutes to speak about. But also we have a very nice batch of other invited speakers. I mean, like Sam Cooper, Professor Shirley Meng, and so on. And in this webinar series, all the project members are going to present in detail the different models and experimental activities that we are carrying out in the Artistic project. Registration here is for free. until now we have 100 registrants, and there is still 200 virtual seats available. Please join us. You are very welcome. Thank you very much for your attention. And I think that now I will move to Carla. I mean, to put this, maybe I don't know if you have some questions. I mean, the audience has some questions. I will be happy to answer before we start with this Mentimeter questions.
I don't see any questions in the chat right now.
Okay.
Maybe they are typing it, so let's leave it for the last time. Now I will be sharing my screen.
Yes.
Yeah. So now you see my screen?
Yes, I can see my face as well.
Yeah, that's your face. So it's the same thing as in the active break. You have the code is posting each of the slides, and now is your turn. Maybe we should wait a couple of minutes for the people to join. Well, I think minute. So you can start with the first question.
Yes. Okay, so the first question is, which are the pain points or bottlenecks in implementing AI or machine learning for data analysis, according to you? So here we have 6 options: lack of data standards, lack of data warehouse, need of very large data sets, so lack of standards in AI techniques, lack of knowledge in AI, or others. So we see that until now, majority of people, they think is lack of data standards and need of very large data sets. Also lack of data warehouse. Yeah, very interesting. Clara, you tell me when we stop the voting. And then maybe I can comment.
Yeah, you can start, I think. It's
Okay.
like stuck. Yeah, you can start right now.
Okay, great. So yes, I mean, what we see is definitely that lack of a data standards is a major bottleneck for implementing AI and machine learning for data analysis, for sure. Also, the need of very large data sets. This is not systematically true, I would say. So in one of the works I show you today, so we were surprised to find that with data sets of the order of 100 experimental points, we were able to develop classifiers. I mean, machine learning models able to classify, you know, the electroporosity as function of the slurry parameters and so on, with an accuracy higher than 80%. Okay. This is was very surprising. So we were not expecting that, but you see, I mean, it's possible also to work with small data sets, right? The problem is that we don't know in advance what is the size of the data sets that we need in order to develop a reliable AI technique, right, or machine learning technique. Definitely lack of data warehouse is another issue. And this is why in the artistic projects, so we are releasing data and related to battery manufacturing. And also we are intending to expand this even more, because I didn't mention, but we are targeting to have 100,000 experimental and modeling points related to battery manufacturing. So release by 2023.
So why do you think is this big misconception of why people think they need very large data sets?
Yes, because this is what is being used. I mean, it's being used to say in press, you know, on this kind of, you know, in general. So also we see very well for image recognition, right? For Facebook or Google image and so on. Definitely these machine learning models are able to recognize faces and images because they're trained with a lot of data, right? And then I think that people believe that, okay, systematically, we need a lot of data to train these machine learning models in a proper way. I would say majority of cases is true, but in some cases it's not necessarily true, right? I can also refer to another example. It's a work being carried out in MIT by Professor Richard Bratz. So also he published a couple of nice papers in the last couple of years when he used, aging curves for 150 cells only, to develop a machine learning model that is able to predict lifetime with very high accuracy, right? This is another example. However, he has a lot of cycles, right? When you are doing performing aging tests, but at the same time, so you only have 150 conditions, right? So it's not too large. So yeah.
Oh, that's interesting. Think we can move on.
Yes, please. Okay, so which are the main expectations regarding the AI for data analysis? Unravel complex parameter interdependencies, accelerate battery and manufacturing optimization, reduction of amount of experimental efforts, predict battery performance, or others. I would say this question is more personalized, right? It really depends on your personal interests, right? The research you are doing or the company you are working in and so on and so forth. It's more to have an idea about your expectations, right? Okay, so until now we see that battery performance prediction, yes, and also reduction of amount of experimental efforts for sure, accelerate battery and manufacturing optimizations, also unravel parameter interdependencies. This is a general problem, right? It can be applied to different scales, right? Even from the synthesis of a material to the manufacturing of electrodes to the cell operation, to the system level integration of the cell, and so on and so forth. We see also unravel complex parameter. Yes, fine. So, and also predict battery performance, definitely. I would say that when we take a look in the state of the art, you see that the majority of papers, they deal with the application of machine learning for battery performance prediction and battery aging or lifetime prediction, right? And in proportion, so the number of applications of machine learning on battery manufacturing is very limited. In part, the reason of that is that there are not widely available, data sets for training machine learning models. So this is why in the artistic project we intend to do that, right? To release these data sets to everyone on battery manufacturing. Others, I mean, it's interesting. Maybe for the people who enter others, maybe you can write in the chat the kind of applications, your expectations you are looking for. I would say other applications is definitely battery recyclability, right? I mean, to make a selection of the batteries once they have been used that you can use in a second life application. There are a couple of papers are reporting this kind of machine learning application. Yeah, but definitely unraveling complex parameter interdependencies is, I will say this is one pillar, right? Because machine learning is very powerful for dealing with multidimensional data sets, right?
Where I can tell you when we saw the participants and in particular the one that picked this session, we saw that it's more or less the same amount of people from research centers and universities and from business. And what do you think about this? What do you think about people? What do research centers mainly have chosen here?
Yes, I think for sure depends on regarding industry. So it depends which kind of industry we are talking about, right? Because maybe people maybe making cells, they will be more interested on battery performance. Maybe others, so you have maybe synthesis of materials, right? They will deal more with amount of experimental efforts, right? Even though nowadays people synthesizing materials for batteries, they are also making their own cells, right? I think we got a comment here. Yes, can you somehow include some physics into your machine learning models? Yes, that is possible. But if you have the physics models In the artistic project, we have them. So we are simulating each step of the manufacturing process using physics-based models such as coarse-grained discrete element method, lattice Boltzmann, and so on and so forth. And then somehow you can, from these models, generate data, right? That is physics-based data that can be incorporated in the data set that you use to train the machine learning model. Right? Another question is from Benoit Mathieu. Thank you for that analysis of multidimensional data. Can artificial intelligence do much more than Kringin meta modeling? So I'm not sure I understand what is your meaning of meta modeling here and Kringin data modeling. Benoit, maybe you can comment. I mean, you can maybe use your microphone. It could be better because we are not so numerous here.
Perfect. So we continue. If you see some hand for participating, maybe we can give the microphone.
Okay. Well, sorry, Benoit, but I will reply. Okay, don't worry.
Yeah, don't worry, it's okay.
You can drop me an email, Benoit. Also, you are working at CALC. Nice. Okay, go ahead. Okay, so what you are doing to reach your goals using AI for data analysis? So outsourcing, service provider, specialist recruitment, partnership with a specialized company, in-house training, in-house department. I mean, that means that you have your own, capabilities in your place, right, of work, or others. This is really a question about you guys. Okay, so we see for now, majority of people, they vote for in-house training. I would say this is something that, as a majority of us, we are forced to do, in particular when you are working in academia environment, because it's a blooming field, right? So many techniques are being developed and very interesting and powerful. And also, what we can observe in the modeling community is that people that are shifting little by little from these physics-based simulation tools to data-driving tools, or tools hybridizing, so physics-based models with machine learning models, right? Definitely, yes. This situation from many people of us. This is something that is, anyways, I will highlight that it's very important also to communicate. I mean, to keep a link with a specialist coming from computational science, because otherwise, some of these machine learning techniques, they can look a bit obscure, right? And it's like the very beginnings of density functional theory calculations, DFT, right? At the beginning, so people that were using DFT as a black box, right? So this is very important also to understand what is behind, right? And what are the limitations. In a machine learning model, you have, for example, many cases, hyperparameters. I mean, parameters that you need to tune, which are, you tune them empirically, right? To fit the experimental data or modeling data you have. So I got here a question from Mona. So thanks for the presentation. Are you using the AI models in an online way or in control loop for battery manufacturing? This is a very good question. So in the artistic project, so we are using for control loop of battery manufacturing. And in the webinar series I was promoting at the end of my short presentation, so we are going to show a device which is based on augmented reality, which is able to control machines of battery manufacturing, such as calendaring machine and so on and so forth, informed from data processing coming from machine learning models. Okay, this is something very new that we are developing in artistic project, and we are going to release the details in the webinar series. For knowing more, you need to attend the webinar series, which is very complementary to the one organized today by the Factor. Okay, so what is machine learning? So, okay, this is a kind of first principles question. I mean, to check that everyone understand what is machine learning, because there is some confusion, in literature sometimes. So the study of computer programs that improve automatically through experience, a type of artificial intelligence, an approach that derives mathematical functions from data, an AI technique based on statistical methods, a deep neural network. Okay, so here you see, till now, majority of people they choose AI technique based on statistical methods and also a type of artificial intelligence, which is correct. Usually, I mean, in literature, we can find a confusion between artificial intelligence and machine learning, right? So machine learning is a subfield of artificial intelligence, right? And there are other techniques beyond machine learning that can be categorized as artificial intelligence. And of course, when you write in a publication, you know, when a presentation, you are doing artificial intelligence is fancy, right? And then this is very eye-catching, right? This is probably why people use artificial intelligence sometimes instead of machine learning. But the most appropriate wording is definitely machine learning compared to what, based on all the things I described today, right? Also, machine learning is kind of a statistical method. For example, you think about principal component analysis, right? And you think about k-means as a supervised machine learning technique can be thought as an advanced statistical method as well. So it's at the end, so you have mathematics so behind, and you are doing analysis of the data. It's kind of statistical like analysis of the data. Also, 17% of people choose the study of computer programs that improve automatically through experience. That's true, right? These computer programs, they can self-correct based on their predictions. I mean, basically, when you have a data set, you divide the data set in a training data set and in a test data set, right? The training data set is used to train the model in a way that is able to reproduce all the outputs contained in this trained data set, if you are doing supervised machine learning in particular. And then so the test data set you use to confront the model, which is now trained, to new data, right? To new input data. And then you will evaluate the accuracy by comparing the outcomes predicted by the model by the ones that you have in this test data set, right? So then I will say that a machine learning model will learn more from failures than from successes, right? I think this is a take-home message for this. And a deep neural network is definitely a type of machine learning model, right? So we say a subclass of machine learning.
And just a quick question: what difference machine learning have with stochastic optimization, for example?
Well, I think stochastic optimization will be something like changing randomly, you know, the parameters and then of your model, right? If you have a model there, that can be also based on a algebraic equation. And then with some optimization tool, so you try to minimize or maximize a given property, right? So it's not necessary, say like this, is not necessarily a machine learning. I will put it as a more, you know, optimization tool, right? But you can have also cross roads between this kind of stochastic approaches and machine learning somehow.
Thank you. Let's move
Welcome.
on to the last question.
So a machine learning model is a computer program that predicts numerical outputs from inputs, automatically extracts information from text, automatically classifies information according to some criteria, self-improve more when it does wrong than right, does not understand anything what is writing here. What is your opinion? Okay, nice. For now it's 25 for each, okay, and 40. Yes, true. For now we don't have, okay, we have 7 people, 8 people voting here. Yeah, we see that doesn't understand anything what is written here. So I will comment about that because when you are doing text mining, for example, so what you will do is you will build a neural network that will recognize entities and also the link between different entities in text. And based on this neural network, so you will be able then to extract the information that you want from a paper, from a document, right? But this doesn't mean that the program understand the meaning, right, of this text, right? So then, so definitely this neural network requires a lot of training, requires to be confront to many type of texts, right? Writing by many different people, I mean, from different origins. I mean, English native speakers and maybe people that, like me, that we are not English native speakers, that maybe we can make some grammar mistakes, or maybe we formulate the things in another way, right? So this is very important because otherwise the data extraction that you will do so will be bad, right? Will be wrong. and you have big mistakes in data extraction. Also, a machine learning model can predict numerical outputs from inputs, definitely. And I show you today one example for the calendaring. I mean, very quickly, when you can predict the impact of calendaring pressure on the tortuosity of the electrode, you can do the same for the electrode conductivity and so on and so forth. Also, we see that 90% of people thinks that it's automatically classify information according to some criteria. Yes, definitely yes. And one example was the one on the slurries I also showed before. Information from text, yes, I already commented about that. Self-improves more when it does wrong than right. Yeah, it's not necessarily always true, this, but yes, I would say it's very important to keep in mind that we need also failure data, right? To train a machine learning model, and it's not only succeed experiments, right? That will be useful for that purpose. Okay. So
Perfect. So we have like a minute, so you can conclude something, and we return automatically to the main panel session.
okay, perfect,
Thank
Clara.
you so much.
Thank you very much for the help, Clara. So, well, to conclude, I will say that machine learning is opening plenty of new perspectives, in particular in the field of battery science and in the field of battery manufacturing. So, and if you are interested in this field, so I really encourage you to put an effort there, because there are plenty of very nice things to do. And I think the key for success in the application of machine learning in battery field is the link between different researchers. Therefore, so what we need is to standardize the way that we report data, battery data. And also we need to create and multiply the number of data repositories, right? To allow, in particular, academic researchers to develop nice machine learning tools that can be useful later on for industry, right? So then I really invite you to go in this direction. And once again, if you want to know more about what we are doing in this topic in the artistic project, please attend the artistic webinar series. And also there you will have the opportunity to listen more about the de facto project, because I really think that two projects are very, very complementary, right? And Elizabeth is doing a great job in that perspective.
Thank you so
Okay,
much,
thank you,
and see you
everyone.
now.
See you now. Cheers.